Ladies and gentlemen, please welcome Lubor Kollar.
Yes, good afternoon. Thank you very much for coming to Denver. Last night I met friends from Australia, friends from Europe, so I know you had quite a long trip, some of you. And I will reward you at this presentation with showing you some index enhancements in SQL Server 2000. And I will be talking about performance improvements. These performance improvements are not like 10, 20%. But I will be showing you techniques which you can use to speed up your queries 10 times, 100 times, or even more. My name is Lubor Kollar, and I am working as a program manager and query processor in SQL Server Query Processor. Query Processor, part of which is query optimization, has lots of to do with indexes. This is the agenda. I will show what I will be covering, how it fits into the DNA context. I will introduce indexes in general, and then I will be going through the particular features which we have added in SQL Server 2000. At the end of the presentation, there will be also a demo, and I will have several slides, best practices slides to help you to deal with your indexing problems. Within the DNA 2000 architecture, what I'm going to talk about is the SQL Server indexes. We have also so-called full text indexing, and that's a separate engine which is running outside of SQL Server, and there will be another presentation on Friday afternoon dealing with full text indexes. So what are the indexes and why do we have them? We have to understand it's all performance. Indexes will not give you any new function, will not enable different applications or different types of queries, but they will give you performance. So the same query with and without using indexes, it's a huge difference. Ideally, you as users would like to see the indexes being kind of invisible to you. You would like to have the performance improvements, but not to pay the cost. Of course, there is always some cost. Then you need a space and on your disk for the indexes, and you need we need to maintain the indexes so they are correct. Overall, SQL Server 2000, the goal is to get increasing performance and lower for as low cost as possible. So first of the improvements in general from comparing to SQL Server 7.0 to SQL Server 2000 is that in SQL Server 7.0, create index is a special command, and the plan for create index in 7.0 is hardwired. What does it mean? You have create index statement, we perform table scan, perform sort, and are building the index. In SQL Server 2000, what we did, we took the create index command and we moved it into a query processor. So now it goes through processing as your other select, insert, delete, or update statements. So it goes through full optimization. What will you gain by that? In the first place, we are building parallel plans on multiprocessor machines. You will see speed up of your create index. And we did measurements, and the measurements show that it's pretty well linear. So on 4-processor machine, you should expect your index build to be 4 times faster compared to SQL Server 7.0. Now, since it goes through optimization, We are looking at other already existing indexes on the table, and we may use those to build the next index faster. And I will show an example of that. Also, now you can specify for each column of the index ascending or descending attribute. So you can have different sort order on different sort direction on different columns. Here is an example. If I assume that I have table and the existing index on columns A, B, C, and I'm going to build another index, I2, on columns B and C. In SQL Server 7.0, while building the index I2, we perform full table scan, do the sort, and build the index. Now, Query Optimizer is costing what is better. Is it better for me to read the whole table, or I can access the existing index I1? And most probably the I1 index needs less IOs and less processing, so we will opt for it. Excuse me. Another example, index I3, if I'm building it on a prefix of any existing index, I may save not only the sort of the scan of the base table, but I may save the sort as well. The creation of such index is very fast, because if I'm creating index on columns A, B, and I have already index on A, B, C, by scanning the index I1 in a sorted order, I will avoid sorting at all for this index. Now, what about ascending and descending? This is not so important feature, but there are queries which we were not able to address by index-only access and without doing a sort in 7.0. Here's an example of a query where I'm ordering on one column ascending and one descending. And so even if I have index on A, B in 7.0, both columns have to be sorted in the same direction. Now I can create an index which will be going on column A ascending, column B descending, column C, it doesn't matter, any direction, and it will be used for the query, and we will save the sort. Now here is a best practices for creating indexes on big tables. The best way to do that is to populate the table without any index. In second step, create clustering index on that table. And the third step, create all non-clustering indexes. These non-clustering indexes you can, in 7.0 we were suggesting start and create them all concurrently, or as many as you can. Now it's not so important anymore because we are on multiprocessor machines using multiprocessors for each index anyway, but still it should work well in both ways. So you can start the secondary indexes one after another, or you can start to run them, create them concurrently. Now next feature which we have in a new feature in SQL Server 2000 is that we allow creating indexes on computed columns. Computed columns, we had computed columns already in SQL Server 7.0. Now we allow to create also indexes on them, and I will give example. There are some conditions which must be satisfied in order to create an index on a computed column. In the first place, the expression defining the computed column must be deterministic. And also there is some business with set options. And I will cover both these issues, issue of determinism and issue of set options in that context later in the presentation. So for now, we know that there is something about determinism, there is something with the set options, and if we satisfy all of that, we can create indexes on computed columns in SQL Server 2000. And I will give you an example. Example, I have a sales table S and a sales date column. If my query is asking for a sales in a particular month, so I have a query which asks for where the month of the sale is December 12th, in SQL Server 7.0, we always needed to perform a scan of the whole table and apply the date part predicate on each row to find which rows do qualify. Now, what I can do in SQL Server 2000, I can add a computed column which I call sales months, and I define it as there is date part, the month date part of the sales date. Then I can create index on the computed column, and then I can write my query where I'm asking for the new computed column sales months to be equal 12. And for this query, we will use index seek in SQL Server 2000. What does it mean? We will go only after less than 10% of data, and we don't need to apply the predicate on every single row. Now, this is the main topic of my talk, and it has to do with index views. I will explain what an index view is. I will show what kind of scenarios can benefit from this new feature. And I will also talk about how to create an index on a view. And I will explain the optimization considerations which we are making in the query processor when considering index views. And I will show some examples and talk about best practices in this context. In the first place, what is an index view? You have heard, I'm pretty sure, materialized views. We call it index views. It's almost the same thing, and it's not the same thing. Why we have chosen to call it index views? There are two good reasons. One reason is that we are truly creating indexes on views, and as you will see. And the second good reason is different database vendors have different coverage for this feature. For example, and different names. For example, Teradata calls it join indexes. DB2 calls it summary tables. Oracle calls it materialized views. And each of these vendors have different flavor of some flavor and different restrictions on the materialized views. So if I'm talking about index views, we know exactly what we are talking about. If I were using the terms materialized views, you are not sure. So therefore, in the context of SQL Server 2000, we are talking about index views. The view which I am going to index may be a join or aggregation or their combination. Now we know that the view today in SQL Server 7.0, it's only a metadata. There is no data behind it until I execute a query which refers to the view. At that moment, I am going to the underlying tables. I perform required joins, aggregations, and other operations, filtering, and so on, and present the view. If I create an index on the view, as I would see it performing select start from the view, suddenly that becomes a table. That becomes a table, and the table is stored in the database as any other table. Since this is an index, even if it's on a view, the metaphor of indexes are automatically and transactionally updated with any changes to the database. And that is true also for our index on the view. So any insert, update, or delete operation which touches the underlying tables of the index views will be performed on the table on all these indexes as well as on all index views which are referring to the table. Now, and the optimizer is using index views similarly as our today's indexes. What does it mean? If your query is using an index, you don't name the index to be used. So it's automatically used by the query, considered by the query optimizer, and chosen based on a costing criteria. The same is true for index views. The index view is an index, and your query doesn't need to refer to the view, neither does it need to refer to the index. What we do, we build a plan for the query, and we have the plan for the index view, and we try to match it in the part of the query, and that part of the query will be replaced by referencing the index view, index on the view. So what workloads will benefit from index views? This feature is targeted mostly to decision support workloads. We are looking at tables with large amount of rows where I perform large scans, big joins, massive aggregations. Those are the best types of queries where the index views may bring the most performance benefit. Also, repeated patterns of the queries are beneficial. This is the same as for normal indexes. If you have 1,000 queries and only index is used only for one of them, you would prefer to use it as often as possible. So in that context, I'm talking about repeating patterns. So what does it mean? It's repeated aggregation on the same or overlapping sets of columns. So I'm doing aggregations on columns A, B, and then other queries are doing aggregation on columns A, B, C, and so on. Also repeated joins. Repeated joins, for example, on a primary key foreign key relationship. So if you have joins of two or three tables which are being used in many queries, you can as well create a view and an index on that join, and it may be efficiently used. And then we can combine these aggregations and joins in our index views. Now, what workloads will not benefit? OLTP systems, we have to be careful in general with indexing on OLTP systems, and even more with index views. A database where I have heavy updates, where the update activities are prevailing because I will pay additional costs for maintaining the index views. Updates in general are more expensive. However, if I have an index on a view which is only a simple aggregation, and I will show such example in my demo, then we are maintaining the aggregation by deltas. So we did some measurements, and for this kind of aggregations, the update cost is similar as for regular indexes. However, if you have joins in your index views, then the update cost may be arbitrarily large because inserting a single row in a base table may result in inserting maybe thousands of rows in the index view. It depends on the type of a join you have. Also, you may have expanding joins. I may be joining two 1,000 row tables, and my result may be 500,000 row table. So it's not very wise to go and to create an index view on the 500,000 row join. Then I can have aggregations on high cardinality values. What does it mean? The extreme case, if I have a unique column in a table, and I aggregate on that column, my result will be exactly the same size as the original table. So if you are aggregating on the combination of columns and the combination is unique or close to unique, then the view will be almost as big as the original table. Now I'm going to talk about how to create index views, indexes on views. The first index on a view must be clustered and must be unique. Clustered, the view is persisted exactly, physically it looks exactly the same way as a table with clustering index. And why it needs to be unique? It needs to be unique because we would like to be able to maintain it efficiently. So if I bring changes on the underlying tables, I would like to be able to efficiently find the row or set of rows which I need to update in that index view. Now, there are some pretty complex considerations which I will explain in the context of index views, but these considerations are common also to indexes on computed columns as well as to user-defined functions, especially to deterministic user-defined functions. So what I will explain the concept of determinism. This is a new thing in SQL Server 2000, and we need it because we are now starting to persist functions and results of functions and so on. Then I will explain a new concept with views. It's called view with schema binding. I will tell and show what it is. And then I will show how we are creating the index and what are we doing in the optimizer when we are considering use of index views. So, determinism. You know, in SQL Server 7.0 we have a whole bunch of functions which are kind of prepackaged functions. And in SQL Server 2000 we are introducing also so-called user-defined functions. So you can define your own functions. And there will be a presentation later this afternoon about enhancements in T-SQL, which is covering specifically user-defined functions. But when I'm defining a function, some functions are non-deterministic and some are deterministic. Good example of non-deterministic function is getData, getDate function. Why? Because I execute it now and I execute it tomorrow or I execute an hour later, I will get different result because I will get the timestamp of the current time. Now imagine that I have, and you can create computed column in your table, or you can create that column in a view, which will refer to this function, getDate function. Now imagine I would come and create index on that column, so I would persist the value as I see it at this moment. And I would come hour later and I would use that index. I would get different result than if I were not using that index. And this is what we don't allow. Therefore, in general, we don't allow indexing non-deterministic functions. And this is true for indexes on computed columns as well as for views which we are going to index, because you can have it somewhere in the view refer to this function in a view definition. So functions like sum, average, plus, minus, concatenation, and so on are examples of deterministic functions. Non-deterministic functions are, for example, date name, because it's language dependent, so it depends on the language context, therefore we cannot index it. Also, rand function is non-deterministic. Actually, there are nodes on this slide which has complete list of all functions in SQL Server 2000, and each of them is marked as deterministic and non-deterministic. There is a little bit trick with strings, string conversions to dates. You can, in SQL Server 7.0 or 6.5 even, and 2000, use a string, your date in a string as a constant in your query. And for example, compare it with a column of data type, date time. Now, to perform that comparison, we have to convert the string into the date time format. And we will do it implicitly. You don't need to do anything. But suddenly, so even you don't have that function coded in your query, because we need to add that function, suddenly that predicate becomes non-deterministic, because the conversion, the result of the conversion depends on the date format. You can always prevent it explicitly coding the conversion into your application. But it's only this is an example, because we are working with early adopters, and this kind of popped up as an issue, not straightforward. They had a query and we thought, oh, it's non-deterministic view. Why it is non-deterministic? It wasn't obvious. So this was a problem. Now, to make things even more complicated, we need to do some consideration on set options. Why? If I have expression, for example, A divided by B, the result of that expression, if I have the same values of A, B, depends on setting of so-called arith abort option. If for example, B is 0 and arith abort is off, the result is null. And if arith abort is on, the result is error. So if I have this kind of expression, A divided by B, in my computed column or in a view, and I'm creating index on it, depending on the current setting of the arith abort, my index will be different. Now that's bad. Therefore, and similar example is also with concatenation. If you have any string and you concatenate it with null, SQL Server can return you two different results, depending on the setting of concat null yields null. It can be either null, if the concat null yields null is set to yes, and if it's set to no, we treat the null string as an empty string, so the result would be the original string concatenated with the null. So we have here a problem. We declare those functions as concatenation or plus or divide as deterministic, and yet we may get different results. To address this issue, when dealing with indexes on views and indexes on computed columns, and also when dealing with deterministic user-defined functions, the following set options must have these fixed values. And these are mostly ANSI-related options like arith abort, concat null, yields null, and so on. So our preferred way is to be ANSI compliant with these set options. If your set options are not set to the values as I showed, the index on the view cannot be created in the first place. then what you can do, you can set the options correctly, create the index on the view, but then eventually change them. But if they are changed, the query optimizer is always sensitive to the set options when considering index views, because we know that if the setting is not correct exactly as required, I might get different result using the index view or executing the query without touching the index view. Therefore, if the settings are not correct, then we will not use the index view. And the maintenance operations, insert, update, delete, are not allowed on the index views if the set options are not set correctly. Excuse me. Well, it may sound kind of complex, so with these set options, determinism, and so on. I will, at the end of the presentation, show a demo, and I will explain and show that you may need to do nothing to get it all right, and why it is that. If you don't touch those 7 set options, you are on your right way to having index views and having everything correct. Why? Because OLEDB and ODBC are implicitly setting these options for you correctly. And it's the same setting as it was in 7.0, so there is no change. The only one is arith abort. The arith abort, and you can set it, and we suggest that you set it on a server level to on using user options if you are using index views. Why? For example, if you BCP into a table which has index view, and this setting is not correctly on a server level, then your BCP may fail because we are not able to maintain the index view. But otherwise, so this is the only thing you need to do. Set the arith abort user option correctly on the server, and you are on your way. Now, another new concept which we have in SQL Server 2000 is schema binding. Views with schema binding, we are distinguishing views without and with schema binding in SQL Server 2000. What you can do now in 7.0, or even in SQL Server 2000 for that matter, you can create a view as simple as select star from a table. Now you can drop the table and recreate the table with, for example, different set of columns, or totally something with different schema. Now, and you do your select star from the view, and you will be presented with different data, for example, more columns. Now imagine that you create index on such a view, and you drop the table underneath, you change the table, and the index becomes invalid. To prevent that, we have introduced concept of called schema binding for views. What does it mean? If I create a view with schema binding, I nail down all columns of all tables which I'm referring to in my view with schema binding. What does it mean? I create a view with schema binding referring to several tables and their columns, and from that moment on, I am not able to drop those tables, remove those columns from tables, alter those columns, so do any change which would jeopardize index view on that index on that view. A similar concept, the same concept is also introduced for user-defined functions, because user-defined function can refer to other user-defined functions or other database objects. And if I want that function to participate in indexes in any way, I must make sure that it's deterministic. So I must make sure that nothing under that function will not change. And that will be again covered in the presentation more about user-defined functions in T-SQL presentation later this afternoon. So, and the condition comes that only a view with schema binding can be indexed. So, now, as I mentioned, we have these set options, preset set options. These set options normally are maintained on our session, which I have with SQL Server. However, some of the objects, for example, views, even tables, they remember some of these options from the time they are created, and they ignore those options on the session and then use the options which are owned to the object. Therefore, to play it safe, already when you are creating your tables, views, even before you go into creating the indexes, you should have those set options set correctly. Now, how is this permission on this schema binding view? Imagine that you have your table, and I will create a view with schema binding on the table, and I will refer to one of your columns. Suddenly, you cannot change the column, and it's your table. That's not fair. So what we require, to create a view with schema binding, the view creator must have at least a reference permission for all the tables in the view definition. So you have to give me at first the reference permission before I create such a view which would bind your table and can make it impossible for you to change the table. One more restriction which we have for the views, for creating indexes on the views, for creating schema-bound views, is that all the underlying tables must reside in the same database. So the concept of schema binding doesn't quite work across the databases because each database is own schema and so on. So as I mentioned, if I'm going to create index on a view, the view must have schema binding. The second, the index must be clustered, must be unique. Now, there are some more restrictions on the views which you can index and which you cannot. For example, subqueries, if there is a subquery, we won't allow you to create index on such a view. It doesn't mean that your query which contains a subquery cannot use index view. It can, but that construct cannot be used directly in index view. Self joins, outer joins, unions, and so on. And books online in beta 2 soon they have complete list of all the restrictions. And also we have one more restriction which has to do with ownership. So as I explained, as a view with schema binding, I must get from you reference permission. But to create an index, suddenly I will access your data and suddenly I will be able to see your data. And there are also some other permission concerns. Therefore, for now we have restricted that the owner of the index of the view, owner of the index, and owner of all the underlying tables must be the same in order to be able to create index. So I have a view, I have underlying tables. If it's the same owner as the same owner which is creating the index, I'm safe. Now, what about optimizer considerations? So I have created indexes on views, and I have my query, and I insist, I'm sure this query will use this index on that view. And it is not. So first thing to look at is at the 7 set options, if you have set it correctly in your session. And we have so-called session property function which you can use to investigate your current setting of any of these set options. Also, what can happen that the optimizer may have discovered the match, but the costing may favor some other index or some other way to process a query. So again, the index U will not be used. And as I explained, we are performing matching on the query graph with the plan for the index view and to trying to find a match. And there are certain situations that even your view definition and its index definition looks very similar, like a piece of the query, we may not be able to find the match. Now we have some hints. As I explained before, the view normally doesn't need to be referenced in the query in order the index to be used at all. But what you can do, if you reference a view and you can use that hint called no-expand to enforce use of the index on the view. What does it mean, no-expand? No-expand, normally if I have a query with a view, when it goes through the processing, I will first replace the view by its definition. I will call it expanding the view definition, and then I'm going through the optimization and so on. Now, with this no-expand hint, we will tell, don't expand that and use it as a table right away. So if you use that index, that hint, and you don't have the index on that view, the query will fail because we couldn't find that index. Now, we have also, in some sense, opposite hint. When I don't want the index views to be considered at all, I can at the end of the query use option expand views, what means that no index views will be considered for the query. So then you can use it, for example, to compare the performance. You can use it with that option and without, and to see how the performance goes. Now, I will give example, a simple example, and there are many more examples in the notes attached to this slide, the PowerPoint slide. So once you get your CD, you can find there are many more examples. All of these examples are on the Northwind database. So you can run it directly on the server as you install it. Here I have an example when I'm selecting top 5 products with biggest discount total. So this is a query from order which is selecting, is a simple aggregation selecting from order details. Now I will show the how looks the view. So as you see, I have to create the view with schema binding. It looks very similar it's very similar to the query to start with. And then I create unique cluster index on that view. And now if I try the query from query analyzer, for example, you will see that the index view is used. The index view you can see in a show plan. Now, we are working with several early adopters who have our beta 1 code or later builds, and we are working on this. This is a production, the results of use of index views on production database. As you can see, the performance improvements are very dramatic. So here, and I will demonstrate one example. And it's because we basically pre-calculate the joins or aggregations. A piece of the work is done up front. So you can get 100,000 improvements which you want from this technique. And these are real production database. Actually, it's MS Sales database, popular from the DOJ case because the lawyers were drilling through the database. So those are decision support queries. The database is heavily used in Microsoft everyday life. It's installed on quite a few servers to get the workload. So therefore, the owners of the database and the servers are quite excited because when they see these improvements, it may prolong the life of their current servers if we can decrease the load on them. Now, optimize the considerations of best practices. I have a query. This is a problem I've seen working with these early adopters. I've seen this problem several times. So therefore, I'm pointing it out and showing the possible resolutions. The first question, how I will find out if an index view is used at all? And the second is what to do if it's not. The first thing, as I explained already, the query plan refers to the index view. Then it is used. If not, it is not used. And it's true for graphical show plan as well as for in text format, if you look at the plan. But if I see that it's not there, I have to investigate. One particular scenario I've encountered several times. People create indexes, views and indexes on views on very small tables. Now we have to understand, our query optimizer is very aggressive in shrinking down the number of cases it is investigating. So if I, during this optimization, find out that I have a plan for this query, which I can execute in maybe 50 milliseconds, I'm not going to investigate what about using some index views or what about using this different join technique, because that investigation itself could be more than 50 milliseconds. So it may happen that your tables and so are very, very small, and the cost, you will see it on the cost. The cost is very small. The optimizer gets out of the optimization as fast as it can. Now, if in general, if you look at the plan of your query and you see that the cost is under 1, there is a great chance that it will not be used. So, and the business of the server-side options, as I have mentioned, and also this is a tricky business, finding the match. We find it or not. It's non-trivial in some cases, and we are trying to kind of address them all one by one, but we might miss some. It's non-trivial to find out why we couldn't find a match. But one way you can look at it is to look at the show plan on the query, look at the show plan of the view, and try yourself to find a match if it can be found. As I have mentioned, the determinism is not only special to index views, it's same consideration for user-defined functions and for indexes on computed columns. And we have deterministic user-defined functions. There must be with schema binding again, and if it's deterministic and with schema binding, we can index it. Who is determining if it's a deterministic or not user-defined function? We are doing it inside of SQL Server. We know exactly, because you can use only T-SQL syntax in this release, so we have full understanding what you are doing in your function, and we declare it, it's deterministic or not. And that's one of the new object properties you can find ask for your function, is it deterministic or not? But in the first place, it must be with schema binding. If it's not, it will be always non-deterministic. There is one catch. The user-defined function, if it references any table, view, or anything in your database, it's non-deterministic. Because we don't have a link between the user-defined view and the underlying table to, if I index the user-defined view, to propagate all the changes. Now, index tuning wizard. Now I will show the demo. I will explain the index tuning wizard using the demo. Here, we see I have a query in the query analyzer. And I will execute the query and I will show how it all works. So the query is executing. On the side, you see the bar. This is Windows Task Manager, and it's showing the performance. Actually, it's showing the CPU consumption. This query is from well-known benchmarks, TPCD, TPCH, TPCR. All these benchmarks have this query. And what I'm doing here, this query is performing a scan of approximately 1.2 million rows, and it's performing aggregation on those rows. Now, you can also observe here down, there is a running time, execution time, which is increasing. Now we have it 48, 49 seconds. Observe also that the CPU usage is very close to 100%. This is because we have done all these improvements in the I/O processing. So even I'm doing scan of large set, prefetching is so efficient that I don't see any slowdowns or any stalks because of I/O waits. So now the query obviously is finished, and we see that it took 57 seconds. I see it here down in the window. Now what I will do, I will, now I should create the view with schema binding. I should create the index on the view and so on. And to make sure that all the set options are correct, that all the syntax is correct, and many considerations. Rather than kind of worrying about all these restrictions and conditions, I will use index tuning wizard. Now, on a query, I will choose the index tuning wizard, and I will ask index tuning wizard to help me with designing indexes for this particular query. Now, as you see at the very bottom, there is a checkbox, add index views. So by default, we choose it. So it will consider also creating index views. So that's obviously a new feature in SQL Server 2000. So I will let the index tuning wizard consider the index views. Now, another choice which I have to do, which tables? Even the query is using only one table. There's only one query, so it doesn't matter. I will select all tables, and the index tuning wizard is now analyzing the database. So and we'll be suggesting the indexes. So what we did for index tuning wizard in this release? First thing you have seen, it does consider index views. And actually, it's already finished, and it recommends an index. So what I will do, and it also it tells me about 99% improvement I should expect. So what I will do, I will accept these changes, and I will tell it, apply it right away. So now the index tuning wizard will be creating the views, indexes, and I don't care. It will do it all for me. So that's one of the improvements. Another improvement is we are introducing so-called super fast mode for index tuning wizard. In this superfast mode, it will simulate you looking at the queries, looking at the join predicates, and designing index without repeatedly going into the engine and asking, okay, what if I do this index? What will be your cost? And so on. So the superfast mode is very fast, may not end up with optimal design, but it gives you the option to have very fast response from index tuning wizard. Also, we are introducing sampling of the set of the queries. So you can sample the set of the queries. You can tell the index tuning wizard, I want 10% or 20% or 5%. What index tuning wizard will do, will go through all the queries, look at the cost of each of them, and will pick 5 or 10% of the worst ones, and it will do that. It will optimize for those queries. Another improvement which we have is that we will have command line interface for index tuning wizard. It's not exactly at this moment clear what all bells and whistles will be there, but there will be command line interface in one way or another in SQL Server 2000. Okay, so now my demo, as you see, the tuning wizard successfully completed. So the index view is created there, an index and view, and everything is done. Now remember, it took us 57 seconds, here is the time, of 57 seconds to run it the first time. Now let's try to run the same query again. Well, I have it 0 seconds. So I will go, now we need to drill down. Seconds are not enough, I need to go to milliseconds. So we have this set statistics time on, so I will run the query with the set statistics time on to start with. I will run the query, and I will go to the messages window to look. Well, still the execution times, they are at the bottom. They are all zeros. Now, it's because we have also caching, so the planned data can be in the cache. So we have these two neat commands, which is, one is dbcc freeproc cache. That command is freeing procedure cache. So it removes everything from the procedure cache. So if the query is precompiled or stored procedure, now it will clean the procedure cache. And the second similar command for all data buffers, dbcc drop clean buffers. Actually, these commands did live, we had these commands already in SQL Server 7.0, but they were not documented. Now in SQL Server 2000, they will be in your documentation and will be fully supported. So now I will run it again, the query. We remember it was 57 seconds. Now I will clean all the buffers, everything, and I run the query again, and it's finished again. And now the time, so here up it is a parse and compile time. So we need to parse and compile, find the match of the index view and so on. But now we are more interested in the execution. So we executed in 29 milliseconds. So now remember, we had this query executing 57 seconds, and now we have it in 29 milliseconds. Homework to calculate how many times faster it is. Now, some people were kind of skeptical, saying, hey, you know, but this is, you pre-calculate the query, and if I change anything on the query, it's all gone, you have to pre-calculate it again, and I cannot keep around all the results of all possible variations. It's not quite like that. And now I will break every rules of demos, and I will change the query. How I will change it, I will, instead of the sum of extended price, I will calculate average of extended price. So the query changed. Yes, I have changed. This will have different result. And I will show, now I will execute this changed query. It's back again. It used the same index on that view. So it's still similar like an index. It's of a universal use. So we are not nailing, this is a query, this is a view, this is an index, and nobody else can use the index. It's not true. You can do quite a few modifications to the query, and the index still can be considered and can be viewed. Now let's look only for the interest. Well, this time it took us 8 milliseconds to, it took us a little bit longer to parse and compile. The match is a little bit crooked now, but we still found it, and it was done in 8 milliseconds. And I can, this is, now you see the 8 milliseconds. Well, I'm not quite sure how long it would be without the index view. I can try that, but it would be around 50 seconds, I'm sure. So you can, it's well over 1,000. Yes, 8 milliseconds, 1,000 times 8 seconds. So it's maybe 10,000 times. So these kind of speed ups you can expect if the index views are used. So at this moment, I will go for your, I will finish the presentation on index views, and I will invite you to come up with the questions. Thank you. Yes, please.
As far as I understand, the set options are the session level options, right?
Yes, the set options are session level options.
Okay, I have a situation here. I'll try to explain. I'll give you the example here. I define a view, and before doing an index, I'll set all the options. I'll disconnect it. Some other user from the query analyzer connects to the server and tries to use the query optimizer. I mean, use the view. Does it use the index at the time?
If the you on your session you create the view, you create index on the view. Somebody else comes with his query, and his set options are not correct. The optimizer will not use the index view.
So basically, if the other user executes a query, he also has to set the set options before he executes it.
It doesn't need to set it because it's usually ODBC or ORDB. You have all the sessions, all the set options there. So if you don't change it, you will get the index view. But you must. The answer is yes. Any other user, it's a set option. So that session has to have all the options set correctly.
Thank you.
Actually, I have a couple of questions. One is the disk storage requirement for this kind of joins or indices. Are they as much as a Cartesian product of the tables involved in views, or?
Okay, if I didn't hear, but the question is, as I understand, what is the disk requirement?
Exactly.
For storage requirement for index view? The storage requirement you can find out very easily because you have the view definition. You can do select count star from the view. It will tell you how many rows will be there, and you can also find out the width of the row in that index view. And that's exactly, almost exactly that's how you can calculate, multiply those two numbers, and that will give you the size of the disk space you need.
The second question is the usage of my database is in a way that I have mass inserts maybe 2 or 3 times during the day, and the rest of the day is basically not much of an activity as far as insert, but lots of read. If I have such a table, should I basically create maybe a view and then drop it when I want to make an insert and then recreate the view again? Is that an option that I should consider?
The question, if I understand correctly, has to do with maintaining these index views where I have you have twice or 3 times a day some inserts coming in or some updates to the underlying tables. The answer is it depends, and you have basically what I suggest that you measure it. But in general, if I have, for example, I'm going to insert 100 rows into a table which is in index view, it's much better to insert it in one batch, in one statement, insert into select from, for example, as opposed to perform one insert after another. Because as I am maintaining the index view, there may be some joins involved, so if I do one row after another, I would need to perform the joins again on each insert. So the batch updates are much more efficient. The estimate of the degradation of the response time depends on the view, how it is defined, and the only way you can, we do cost it, so you can look at the cost of the update statements, or the inserts and deletes, and the best way to measure it. Okay, thank you. Yes?
Hello. Hello.
Yes.
And a question, please. Definitely using indexes on these views means that we are having result sets made persistent as new tables in database, right?
Yes.
So when you fine-tuned your, modified your query in the tuning, after the tuning wizard demo, changing from the sum operator to the average operator, did it mean that again we had another result set made persistent as a table?
Okay, the question is that I have changed the sum into average, if it did change the result set. Not quite. The trick is, in this case, you saw the query, you didn't see the view. I didn't show you the view, I don't care about, index tuning wizard took care of that. But basically what we are doing, average is the same as sum divided by count, okay? So we can derive, if I have sum, I can derive average, if I have sum and count. As well as so my index view is not exactly as was this query. The index view is slightly different, and I can show you how the view is defined there, but I didn't, even if I store the result, we have still ability to kind of put some operators, for example, on top of it or around it, so we can derive some other queries from the same index view, addressed with the same index view.
Okay, but definitely after the first execution, there has been a new table, is that?
No, that was addressed by a same view. The view had a sum and count, and if it has sum and count, you can have in your query average or sum or none of them, and I will be still able to use that view.
Okay, thanks.
Welcome.
You had mentioned that if in case when you're doing an insert and that causes the index view to fail because somebody changed the set options before the insert update, does that failure show up to the client side so that the table didn't get updated either, the underlying table?
Yes, that's true. It's normal. Insert failed, it will show to client, insert failed.
So the insert does not happen on the underlying table either?
Yes, the insert completely fails, so because there is a link between the table and the index, and it's all transactional, so the index doesn't happen at all.
Thank you.
You're welcome.
If an index view has been created because there are several joins on the same tables in the same fields, is it important for all the subsequent stored procedures to list these tables in fields in the same order as what the index view was created as?
The question is that if the index view has the certain order of columns in its definition, if it's important that subsequent queries or stored procedures, anybody who would in these queries have the same order of the I'm assuming you're talking about select list, select and the list of A, B, C, D, and so if it needs to be the same in order to use the index view, and the answer is no. You can have it, you can change the order. I can do it here on the query, on the demo. I can change the order of the columns in the queries, and the same index view will be used.
Okay, thank you.
You're welcome.
Yeah, question from the web here. I'll read it verbatim. By creating an index on view, the table is persistent. What is the difference between this and creating a second table and setting up triggers to update the second table as the main table is updated? Are there performance gains?
Okay, everybody heard, yes, the question. I will repeat the question basically. The alternative is to create completely new table, populate it as if it were the view with the same data, and then put in place triggers and maintain the table correctly through the triggers. The performance will not be better with this solution, definitely. And one problem which you will need to refer specifically to the new table. What I was showing in the query here, and in general, what is true for index view is that that index or that view doesn't need to be referenced at all, and we will find the match. Since this table, separate table, is totally separate, so you would need to change your query to refer to the table. Okay.
Can one create an indexed view on where one or more of the underlying tables comes from a remote server?
The question is if it comes from a remote server. No, you cannot. The restriction is even worse. You cannot create index view if those two tables are in different databases. It's because the concept of schema binding is restricted to a database at this moment.
Even if you don't use schema binding?
Pardon me?
Even if you don't create the view with schema binding?
If you create the view with schema binding, we will not allow you to create index on that view. So the schema binding is a necessary condition to create it. Okay.
Are the index views governed by the same locking rules as a non-clustered index, for instance?
The question if the index views have the same locking rules. Yes, it's true. The index views have the same locking rule. Once I create the index on a view, it's exactly as any table with cluster index.
If I insert a row that doesn't match the where clause on a view, so I'm inserting to the base table, I understand from what you said about the disk space cost that there will be no disk access cost on the insert for the index on the view, since the row will not appear in that view.
The question is if there is where clause which eliminates the row from the view, then it's true. There will not be any activity on the view, in that case, or on the index on that view at all, because you don't change the data set in that view.
Question on computed columns. In your example, you referenced the computed column name. Now, would the optimization still occur if you reference the expression that was used by, or the similar as your index views?
That's a very good question. Not in this release is the answer, but we are pretty close. But okay, thank you very much.